Okay, today we'll begin, as it says on our schedule, empirical molecular formulas, page 245. If you would please. Okay, these formulas on page 245. When a new substance is synthesized or discovered, it is analyzed quantitatively to reveal its percentage composition. The difference between qualitative analysis and quantitative is two different branches of chemistry, because when you deal with quantitative, you're not only just identifying what element is within a substance, but also how much is also within that. Qualitative, you're just identifying, okay, this is sodium, this is maybe iron. Some of the metal ions in your analysis that will be taking place, maybe, trying to think, sometime, it usually happens right before Thanksgiving, somewhere in where we're probably, we end probably right before Thanksgiving. And then that's about when we start our final chapter, or chapters, whether it's balancing reactions and start some stoichiometry yet this semester. But regardless, this is a quantitative analysis. Okay? From these data, the empirical formula is then determined. An empirical formula consists of the symbols of the elements combined in a compound with subscripts showing the smallest whole number ratio of the different atoms in the compound. For an ionic compound, the formula unit is usually the compound's empirical formula. For a molecular compound, however, its empirical formula does not necessarily indicate the actual numbers of atoms present in the molecule. For example, the empirical formula for the gas dibromine is BH3. And the reason that we called it, I say that, yeah, diborane, not bromine. Diborane has one atom of boron and 3 atoms of hydrogen. But the molecular formula, B2H6, okay, in this case, the number of atoms given by the molecular formula corresponds with the empirical ratio multiplied by 2. So what happens in these, sometimes when you calculate the empirical formula, it still might not be the correct analysis. You may have to compare that to the molecular formula, which does not mean anything to you right now until we do some of these examples. Okay, so there's always sample problems for you to read through that you can do on your own time. It shows you how to do those, but it's not going to tell you why you do those certain steps. Okay, we look at the top of page 246. Because of rounding or experimental error, a compound's mole ratio sometimes consists of numbers close to whole numbers instead of exact whole numbers. In this case, the differences from whole numbers may be ignored and the nearest whole number taken. Thus, diborane contains the atoms in a ratio of 1 to 3. The compound's empirical formula is BH3. Sometimes the mass composition is known instead of the percent composition. To determine the empirical formula in this case, convert the mass composition to composition in moles, then calculate the smallest whole number ratio of atoms. The process is shown in sample problem M. So in this case, this is a lot of what you had done last August and September. But you have to take the analysis a couple steps further. So what is it that we did in early September? We just took a mass in grams and converted it to what? Just to moles. So that's what we had done last September. Here, you actually have to compare the smallest ratio that we see to calculate the empirical formula. Now, why is something like that important? Well, a couple things. One is you're going to have to be able to do this in college, because we do refer to this as a college prep class. And two is we take the approach that you're going to be forensic scientists. And with that, you would have to be able to explain quantitatively what a lot of this information needs, because anybody, of course, can take a solution and can put it into a gas chromatograph, and that's going to do all the analysis for you. When we did the hunting the elements video when you were freshmen, they showed a forensic chemist who could identify different types of blast patterns. And one of the things, if you remember what might stand out, do you remember they blew up a toy clown at the end? That's what might stand out in your mind. Maybe not the video itself. Maybe this isn't registering at all. No, not at all? Okay. But that's the approach that we take, is that rather than just letting the computer do that, as a forensic witness, we would want you to be able to describe the analysis. Please stop that, whoever's doing it. Okay? So what happens is you could mathematically do these calculations, and that's why we would want you to be able to sit on the witness stand and be able to explain to potential jurors, okay, this is the analysis of this compound, and that's what this means. The computer can't do that. It will show you a readout, but it's not going to say why that has different components for it. Here, you do the mathematical portion of it. So again, it doesn't make any sense to you now because you haven't been taught this yet. Bring back fond memories, Mr. Wagner?
Of course.
Of course, that's right. So again, when you look at sample problem L, that says sample problem M as well, one of the things that we see here, let's just look at page 246, it says quantitative analysis shows a compound contains the percentages of sodium, sulfur, and then oxygen. So about 32.38% sodium, 22.65% sulfur, and 45% oxygen. So in each and every one of those cases, you change that grams, you just presume that all those numbers, they add up to 100. Okay? So with that, you change the percentage to grams, and that's what they're showing you at the next portion of the problem solving. They take that 32.38% of sodium, change it to grams, so 32.38 grams of sodium. Then where does 22.99, but we would use 23 grams of sodium. Where would that number come from? The atomic mass of sodium. You do the same thing for sulfur. You do the same thing for oxygen. And what happens is you are converting those grams to moles, just like what we did in September. Then you find the smallest ratio of those, divide them into each other to give you your empirical formula. Again, none of that means anything to you right now. So the sample problems show you how to do it, but doesn't explain why you're doing these separate steps. So in this case, let's go ahead and look at one of the practice problems, okay, on page 247. Again, I just leave, you're responsible enough to read through these sample problems if you think you need more help with those. Okay, so letter A, or no, not letter A, number 1 on page 247, this is the practice problem portion. It says a compound is found to contain 63.52% iron and 36.48% sulfur. Find its empirical formula. So we know that the analysis of this substance says that we've got iron and we've got sulfur. Okay? So that's all we know that's in this compound, but it gives you the percentage breakdown. So once you see those percentages, okay, it says 63 and 36, those two numbers added together is going to total 100. So go ahead and take 63.52% iron and change that to grams. So 63.52, not percent, but now grams of iron. Okay? And then we're going to change that to what, do you think? What did we do in September? Moles. Change it to moles. So for every mole of iron, how many grams of iron do we get? So That is exactly what you're doing. That's correct. Okay, so upon doing that, just like what we did in September, or you could say August, I guess, 63.52 divided by 55.85, which gives us 1.1. I would say go out 3 decimal places, okay? So we always say round to the nearest hundredth, but we're going to go 3 decimal places, 1, 3, 7, okay? Now that's moles of iron, okay? We're going to do the same thing for our sulfur now, but in this case, it's not 36.48%, it's actually grams then instead. So 36.48 grams of sulfur. We're going to change that to moles of sulfur, just like what we would have done up there for every mole of sulfur. How many grams of sulfur do we get? Okay, so one of the things we see happening, that's pretty close to 1. It probably comes out to, I don't know, 1.0001 maybe, 36.48 divided by 32.07. That gives us, 1.137. 1.137. Now that is moles of sulfur. So we don't add these up. We look at these, you find the smallest number, right, and you would divide them into each other. So this is our molecular form, or excuse me, our empirical formula. We don't have enough information to determine if this is the correct molecular formula. There you'd have to be given the substance's grams per mole, its molar mass. But we don't have that, so it doesn't ask you to take that extra added step. Pretty simple.
So those are the empirical formulas.
This is your empirical formula right here, and how you would calculate it.
So you just write FES.
This is it right here. I'm sorry, repeat your question again.
So like what's the boxes, like what's in the box, that's your
This is your answer right here. Okay?
And why do we do all that other stuff?
Because these came out as 1 to 1.
You do one where
What
it
if it
doesn't
doesn't
come out
come out?
equal.
That's exactly what we're going to do. Okay?
Yeah, what happens if it doesn't come out?
Well, we'll encounter that when we get there. Okay? So, letter, how do I want to say letter? Number 2. Okay? It says find the empirical formula of a compound found to contain 26.56% potassium, 35.41% chromium, and the remainder is oxygen. Okay? I'm presuming that we're discussing everything that's up here, right, gentlemen? Okay? You mean Hamas? You don't even know what Hamas is, do you?
Yeah, it's a terrorist group.
It is. I think. I don't know. I just heard the term Hamas. I don't know what it is either. I was just seeing if you did. But you didn't know that. But turns out you did maybe. Okay. So here, see, I got the teacher's book here. So I can just write this up, K2CR2O7. So this is going to be your answer. Okay? So we know we got to make our way to that corner. Okay? So if your mass spectrometer or gas chromatograph spits out this information, it said 26.56% potassium. Okay? How much sulfur was there in grams?
5.41.
Okay? And you're correct, but how would you know that it's 38 grams?
That's chromium, it's not sulfur.
Oh, that was from last problem. We were just seeing if anybody's paying attention. Okay, And then how did you know how much oxygen there was?
Remainder, so you gotta add them.
Right. So you have to add these two numbers together, and you would presume that every sample you're dealing with adds up to what? 100%. So once you've done that, and you add these two, subtract from 100, and you get what?
38.03
And that's grams of what?
oxygen.
Okay. So we will let you fill in these gaps here. Okay. And then because though the hard part's done. Okay. Well, maybe not quite all the hard part, but we want you to get moles of each substance.
That's it. That's old faster you can go in yours.
You going by Lone Tree?
Okay, so I would presume that everyone's got an answer for this. Is that 50, 52? I think so.
Curiosity and Berlin.
Okay. I'm also presuming that we know how to do this then. Would that be correct? Okay. Well, I am going to ask a fellow like you. So what do we get here then? You got a calculator. Okay, why don't you grab it quick?
A shocking discovery.
Say 39.6.
Yeah, 0.67.
0.67.
679. 679.
Okay. We're going to leave it as this then.
681.
Okay. What about our chromium then?
0.681.
That's what you get?
And
Okay.
then no, it's 2.377.
Okay, once you get to this step, just like the prior problem, you find the smallest one. Okay, so in either case, you know, these are pretty close to one another, but we'll still pick this one. Okay,
Wait, so say you get to like if you round that to 6.8 and the one on the bottom 6.82, what would you do?
well, we're going to look at it this way. Okay, we'll come back to your question. I'm not ignoring you. Okay. So if that's what we think our smallest number is, we would do the same thing here, and then you do the same thing down here. Okay? The reason we say that is we wanted to leave it like this because even when you divide that out, 0.679 divided by 0.6. Oh, I meant to do that one. Okay? 0.681 divided by 0.679. Notice you get 1.00. You're going to go out 3 decimal places and still come up with an answer of 1. So when you do that, these are going to be so close together anyway that gives us 1. This will give us 1. And when you divide these two out, we get what? Say that again.
3.500.
Okay, so what that means is when we look at this analysis and what we told you the answer is, we can't leave an answer on a half, okay? You don't round it up. You don't move your decimal either, okay? Because once I tell you, you're going to say, I knew that. When we look at ones, they're not ones, they're changed to what? So then what happens if you have 3.5? What happened from here to here? You got to double it because it has to be a number that's not a fraction. Okay? So if they come out on halves, you double them. If they come out on quarters, you take it times 4. If they come out on a third, you take them times 3. Now those don't happen very often. Usually halves are the most common. Times it by 2. Correct. Okay? So that is how you determine any substance's empirical formula is you convert them to moles, find the smallest one, then divide them into each other.
So if you double one, you got to double all.
You have to double all of them. That's correct. Okay? Do you want to try practice problem number 3 on your own? Go ahead and try that, and then we'll point you in the right direction if we don't get the correct answer.
All right. The question is, analysis of 20 grams of a compound containing only calcium and bromine indicates that 4 grams of calcium are present. What is the empirical formula of the compound? 4 grams of calcium. Yeah.
And then 16 grams of bromine.
Yes.
And then, yep. And 16 grams of bromine, you say? All right, now what?
You have 40.08 grams of calcium.
40
Yeah.
grams per mole?
Yeah.
Okay. So, right here, I write 40, correct?
Yeah.
Is that what you're saying?
Oh, yeah.
And then per 1 mole calcium. All right, how about down here?
79.9.
79.9 grams of bromine. 1 mole. All right. Go ahead.
You divide 4 and 40.08.
You get what?
0.099.
0.099.
Yeah.
Okay. Moles of Ca. Okay. How about this?
0.200.
0.200 mole bromine. All right. Now, how do I find how much of each I need?
You got to divide that by 0.099.
Okay. Both of them. All right.
You get 1 and then you get 2.
Equals
It's like
1.
1.8, so
Oops.
just 1.
Just 1. Yeah. Because these cancel out, right? And then 0.099. Okay, we'll do some rounding. We'll just round that down. So, if I have calcium, and bromine, how many of each am I going to have?
2 calcium and 1 calcium and 2 bromine.
1 of calcium, 2 of bromine. And you don't really need to write the 1, but there you go. Easy money.
And we say that, and that's great. So we all seem to be on the bus. Is that a correct presumption?
Yeah, I'm thinking of watching this.
Flip them back.
Okay, this next problem that we're going to do, when you have to find molecular formulas, do you remember what is the best way to describe the difference between molar mass problems and percent composition problems? Do they have anything in common?
Yeah, they're like set up the same.
Yes. So they're set up the same is exactly right. So molar mass would just be saying, okay, if we had 85 grams of calcium bromide, how much of that is bromine? What's the mass in grams of bromine from all that? There's 4 steps that we correlate. That was the second paper that was handed back to you. Percent composition, however, would be if we have 80 grams of calcium bromide, what is the percent composition of that bromine? That's just one extra added step. This is just the same. Okay? This is just the same. There's one extra added step when we do molecular formulas. Okay. So, this is at the back of your chapter, page 253. Now, whether you choose to follow along, that's entirely up to you, but it just says a compound with a formula mass of 42.08 atomic mass units is found to be 85.64% carbon and 14.36% hydrogen by mass. Find its molecular formula. Okay? 253. Okay? So we have to do the same thing. Find your empirical formula first. Okay? So page 39 on page 253. Okay? So you're still going to do that the same way. You still have to convert your grams to moles.
This is basically the same question.
We got 85.64 carbon.
Okay? So we have 85, what'd you say? 0.64 grams of what?
Carbon.
Carbon. So what we can presume here, 39, okay? This, we know there's carbon and we know there's hydrogen, but we don't know what the ratio is, okay? So now we got 14.36% hydrogen,
That's like 1,
okay? So just like what we've been doing, okay? Is this what they do in college, Mr. Wagner? They do this instead. Which one do they do?
It's been a while. I've always done it that way. I don't think I've ever done it
Okay.
that way, so.
Because to me, this makes the most sense. Not only the most sense for us, but to be able to describe that to yourselves. Okay, so same thing. You're going to convert that to moles. Okay? So what number would go down here?
14. I mean 12.
Yep, so 12.01.
Then 1.
Yeah, 1.01. So you're still going to come out with however many moles of carbon, which is a little over 6, I suppose, if my math is correct.
7.077.
Okay. 7.477, is that right?
7.11.
7.13.
3.
7.1.
Oh, I forgot that.
How about we just do it ourselves then? Okay. 5,
Someone forgot how to use the
6,
calculator.
4. No, they just punched in a wrong number. It's easy to do. 7.1307. If this class was easy, everybody would be in here, right? But not all of your classmates are in here.
Because they want to take.
It doesn't matter what they want to take. We're not concerned what they want to take.
The bottom is 14.217.
Where did you get that 7?
14.327.
That's just the next decimal. Yeah.
Okay?
No, it's not.
So, you found your smallest number up here, which would be which one of these two? It would be carbon. So then, of course, this one's easy to do. You're going to get 1.
The bottom one you get 2.
Be at 1.19.
So 7.1307. And once you divide that out, you get approximately what?
1.9.
Okay, which means this is pretty close to 2. Okay? So, right now it looks like this is what our answer would be. But we have that extra number yet that we have not dealt with. Because in the problem, now you would be given this information. That's the only way you can solve this. It says a compound with a formula mass of 42. It says atomic mass units, but that's just a fancy way of saying grams per mole. Is found to have 85.64% carbon, 18.36% hydrogen. So what that means is this is our empirical formula. Okay? Equals that. Our molecular formula, however, maybe it will match the same as the empirical formula. Sometimes it does. Okay? So what happens when we add all the atomic mass numbers from our empirical formula? Because carbon has a mass of what? Okay? And then how many hydrogens do we have?
2, 1.01.
Okay?
14.030, that's kind of what I'm getting.
Why, I don't know why I put a 1 there. Okay? So, what that means is our empirical formula mass has 14.03. Our molecular formula, which may or may not be right, means we solve this by saying X equals our molecular formula mass divided by our empirical formula mass. Okay? So we've already determined this to be 14. Okay? So what was given in the problem? 42 grams per mole. So that goes on top. Your 14.03 goes on the bottom. So we get X to be what?
0.08.
How much?
It's 42.08.
42.08. And we divide them,
2.9999.
okay, which means that's pretty close to what? So therefore, this is telling us our empirical formula is not the correct molecular formula. Because the gas chromatograph or the mass spectrometer says when we spit this out, the molecular formula mass for that is 42. So the correct molecular formula for that then is not CH2. That's just the simplest ratio. That's an empirical formula. So the correct molecular formula, as you're saying, is C3H. That is what we're looking for. Okay? So this is just having that one extra added step. Just like your molar mass problems and percent compositions, there's just one extra added step you had to take. This case, it's the same thing. You have to find the empirical formula first, and then one extra added step to find the molecular formula. Okay, so tomorrow we'll have problem solving over this. And don't forget, we will have your first problem evaluation on Friday. It's naming chemical formulas and being able to add up their atomic masses. We'll catch up to you next time.